Astronomers only began to comprehend what the Milky Way truly is when they discovered its infinite sisters and cousins across the universe in the early 20th century. This was made possible through telescopes equipped with photo chambers, leading to the realization that our galaxy spans about 100,000 light-years in diameter. Now, a new discovery has emerged, a mysterious glow within the Milky Way. Since 2009, astronomers have been puzzled by an unusually bright light emanating from the heart of our galaxy, a phenomenon that cannot be fully explained by known light sources. Initially, scientists speculated that this could be a sign of dark matter, the invisible substance believed to permeate the universe. However, new studies suggest another possibility: gamma rays emitted by a group of faint, rotating stars known as pulsars, which are currently undetectable with existing telescopes. The Fermi Gamma-ray Space Telescope has played a crucial role in analyzing this mysterious excess of light. Most gamma rays in the Milky Way are produced in the gas between stars, where they are illuminated by cosmic rays. These rays, originating from supernova explosions and pulsars, create a diffuse gamma-ray glow throughout the galaxy. A 2015 study by MIT and Princeton researchers concluded that the excess gamma rays are likely due to pulsars, not dark matter. Despite the pulsar hypothesis, some scientists still suspect that dark matter might be responsible for the surplus gamma rays observed at the galaxy's center. The prevailing theory of dark matter, known as cold dark matter, CDM, explains much of the universe's structure. However, before confirming the presence of dark matter, scientists must rule out all other possible cosmic processes that could generate gamma rays. A massive black hole resides at the center of the Milky Way, and its behavior raises intriguing questions. An international team of researchers has discovered dense, cold gas being ejected from the galaxy's center like bullets. This gas ejection could be the result of either the black hole or the numerous massive stars in the region. The discovery has prompted further investigations into the dynamics of the Milky Way's core. The wind at the Milky Way's center has been a topic of intense debate since the discovery of the Fermi bubbles, a pair of giant spheres filled with hot gas and cosmic rays, about a decade ago. The ejection of mass from the center could deplete the material needed for star formation, potentially halting the birth of new stars in our galaxy. This raises concerns about the future of the Milky Way. A team of South African, Japanese, and Italian scientists has discovered a vacuum in the middle of the Milky Way, where no Cepheids, giant stars with variable brightness, exist. Our galaxy, with a mass equivalent to 4.3 million suns, lies in the direction of Sagittarius, about 26,000 light-years from Earth. At its center is the massive black hole known as Sagittarius A*, hidden within a dense complex of molecular clouds and stars. In about 4 billion years, the Milky Way will collide with its nearest neighbor, the Andromeda Galaxy. Although this cosmic event might sound catastrophic, Earth is expected to survive the collision. The resulting galaxy merger will create a new, intensely starry night sky, transforming the Milky Way into a new galactic entity. Our galaxy is a flat disk, about 100,000 light-years long and 1,000 light-years wide, with the Sun and its planets located 26,000 light-years from the turbulent galactic center. The Milky Way's spiral structure was not always as we see it today. It grew by consuming smaller galaxies, with the Sagittarius elliptical dwarf galaxy being one such victim. The Milky Way is embedded in a vast cluster of dark matter, a substance much larger and more massive than the galaxy itself. In the late 1960s, astronomer Vera Rubin observed that stars at the edge of galaxies like Andromeda were moving at speeds that should have flung them into space. Yet, they remained bound to the galaxy, held together by the gravitational pull of dark matter. At the heart of the Milky Way lies Sagittarius A*, a supermassive black hole with a mass 4 million times that of our Sun. While it cannot be observed directly due to the thick clouds of dust and gas that surround it, astronomers have inferred its presence by studying the orbits of nearby stars. This black hole is thought to be the most powerful particle accelerator in our galaxy, contributing to the mysterious gamma-ray glow. Discovered in 2010, the Fermi bubbles are one of the most perplexing features of the Milky Way. These enormous, balloon-like structures extend about 25,000 light-years above and below the galactic plane. Filled with hot gas and cosmic rays, the Fermi bubbles emit gamma rays, which were detected by NASA's Fermi Gamma Ray Space Telescope. The exact origin of these bubbles remains a mystery, but they are thought to be the result of powerful energy outbursts from the supermassive black hole at the galaxy's center or from intense star formation activity. The energy required to create these structures is immense, and their discovery has led to new theories about the dynamics of our galaxy, including the possibility that the Milky Way's central black hole was once far more active than it is today. The Milky Way, like other galaxies, has undergone a complex formation and evolution process. It began forming around 13.6 billion years ago, just a few hundred million years after the Big Bang. Initially, it was a small, irregular galaxy that grew by merging with other smaller galaxies and absorbing their stars, gas, and dark matter. These galactic mergers contributed to the growth of the Milky Way's mass and helped shape its current spiral structure. Over billions of years, the galaxy developed its characteristic disk, bulge, and halo. The disk is where most of the galaxy's stars, including our Sun, reside. The bulge is a dense region of stars surrounding the galactic center, while the halo is a spherical region that contains older stars and globular clusters. Understanding the Milky Way's formation helps astronomers trace the history of the universe and provides insights into the life cycles of galaxies. Surrounding the Milky Way's disk is a vast halo of stars, globular clusters, and dark matter. This halo is much less dense than the disk but contains some of the oldest stars in the galaxy, many of which are part of globular clusters, spherical collections of tens of thousands to millions of stars bound together by gravity. These ancient stars are remnants from the early stages of the galaxy's formation, providing clues about the Milky Way's history. The halo also contains a significant amount of dark matter, which exerts a gravitational pull on the stars, influencing their orbits. Despite its importance, the galactic halo is difficult to study due to its diffuse nature. However, recent observations have revealed that the halo is not as simple as once thought. It contains streams of stars that are remnants of smaller galaxies that were torn apart and absorbed by the Milky Way. These streams, along with the halo's dark matter content, are key to understanding the galaxy's evolution and the nature of dark matter. Star formation in the Milky Way is a continuous process, with new stars being born from the collapse of dense regions within molecular clouds. These clouds, primarily composed of hydrogen gas, are scattered throughout the galaxy, particularly in the spiral arms. Some of the most prominent star-forming regions include the Orion Nebula, the Carina Nebula, and the Eagle Nebula, home to the famous Pillars of Creation. These regions are often sites of intense activity, where massive stars are born, live short and violent lives, and then explode as supernovae, enriching the surrounding space with heavy elements that will eventually form new stars and planets. Star formation is not evenly distributed across the galaxy. It is concentrated in regions where the density of gas is highest, particularly in the spiral arms. The Milky Way's star formation rate is currently estimated to be about 1 to 2 solar masses per year, meaning that on average, 1 to 2 stars the size of our Sun are formed each year. The Milky Way is not an isolated galaxy. It is part of a much larger structure known as the cosmic web, which consists of vast filaments of galaxies, clusters, and dark matter stretching across the universe. Our galaxy is located within the Local Group, a collection of more than 50 galaxies, including the Andromeda Galaxy and the Triangulum Galaxy. The Local Group itself is part of the Virgo supercluster, a massive collection of thousands of galaxies. Even larger than superclusters, the cosmic web is the largest structure in the universe, connecting galaxies and clusters through dark matter filaments. The Milky Way's position within this cosmic web influences its interactions with other galaxies, including the future collision with Andromeda. These interactions are key to understanding the large-scale structure of the universe and the role of dark matter in shaping the cosmos. The cosmic web not only determines the distribution of galaxies but also influences the formation and evolution of galaxies within it, including the Milky Way. The Milky Way is not only a vast collection of stars, gas, and dark matter but also hosts a complex and pervasive magnetic field. This magnetic field threads through the galaxy, influencing the movement of charged particles and playing a crucial role in various astrophysical processes. While the magnetic field is weak compared to the Earth's, it is still significant enough to affect the behavior of cosmic rays and the interstellar medium. The origin of the Milky Way's magnetic field is thought to be linked to the motions of conductive materials, such as ionized gas, within the galaxy's rotating disk. These motions generate and maintain the magnetic field through a process known as the dynamo effect. The magnetic field helps to shape the structure of the galaxy, influencing the formation of molecular clouds and star formation regions. It also interacts with cosmic rays, guiding their paths and contributing to the diffuse gamma-ray background observed in the galaxy. Supernovae are some of the most energetic events in the universe and play a vital role in the evolution of the Milky Way. These colossal explosions occur when massive stars reach the end of their lives, either through the core collapse mechanism or the thermonuclear explosion of a white dwarf in a binary system. Supernovae serve as a cosmic recycling process, ejecting heavy elements such as iron, oxygen, and carbon into the interstellar medium. These elements are the building blocks of planets, moons, and even life itself. The remnants of supernovae, such as the Crab Nebula, continue to emit radiation for thousands of years, providing insights into the physics of these powerful explosions. Moreover, the shock waves from supernovae can trigger the collapse of nearby gas clouds, leading to the formation of new stars. Thus, supernovae not only mark the death of stars but also contribute to the birth of new ones, ensuring the continuous evolution of the Milky Way. One of the key discoveries that revealed the existence of dark matter was the study of the Milky Way's rotation curve. A galactic rotation curve plots the orbital velocity of stars and gas in the galaxy against their distance from the galactic center. According to classical Newtonian mechanics, stars further from the center of a galaxy should move more slowly than those closer to the center, where the majority of the mass is concentrated. However, observations of the Milky Way, as well as other spiral galaxies, show that stars far from the center orbit at nearly the same speed as those closer in. This flat rotation curve suggests that there is far more mass in the galaxy than can be accounted for by visible matter alone. This unseen mass is what we now refer to as dark matter, which is believed to make up about 85% of the mass of the universe. The study of the Milky Way's rotation curve has been pivotal in our understanding of dark matter and its influence on galaxy formation and dynamics.